your outcome and the probability of each outcome. And we saw one special case so far, the binomial distribution. So the binomial was when we had a set number of outcomes, or set number of trials, only 2 possible outcomes, and everyone was independent. And then we were using our table. Well, it turns out there's some other common distributions. We're going to touch on a couple today. First thing I have on here is just a definition. When I say a probability density function, it's a PDF. It's just an equation that we use to find our probabilities. Okay? We can, if we think about graphing our probabilities, we know that all the probabilities have to add up to 1, and every individual probability has to be between 0 and 1. So when we're looking at a graph, the total area is representing the total probability, which would be 1. So if we're looking at it in a graph, the area under the graph is probability. So the total is 1. And the height at any given point, the probability at any given point has to be somewhere between 0 and 1. Okay, so those probabilities, or those rules are still true. The uniform distribution is not one that comes up very often. I'm going to show an example, but it is not one we will use very much at all. This is a situation where every outcome is equally likely. Okay, and we've seen some of these before. Like if I roll a dice, how many outcomes are there? 6. Doesn't each outcome have the same probability? What is the probability of each of them?
1/6.
1/6. So if you drew a graph for rolling a dice, your x-axis, you could get 1, 2, 3, 4, 5, or 6, and every one of them would have a probability of 1/6. It's the same all the way across. That's uniform. Here's another one. Suppose the United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So the delivery could be at 10 a.m., so when x is 0, or 11 a.m., that's 60 minutes later, so that's when x is 60. With all 1-minute intervals of time between 0 and 60 equally likely, draw a graph. So we are drawing the most basic of graphs here. What is my smallest possible x? 0. What is my biggest possible x? Yeah, so we're doing between 10 and 11 a.m., but it said to do 1-minute intervals. So we can go up to 60 minutes. The probability. How did you get that? So the length of this interval is 60. Total probability is 1, so the probability of everything is 1 out of 60. So it's basically just like a rectangle. The height all the way across is 1 out of 60. No matter where you fall, you have the exact same probability. Now, could we be more accurate in this graph? Absolutely. Could I put more points on my x-axis and show every 1-minute interval? Yes. We just don't necessarily have to, unless you chose to do that. If I had said it can only happen between 30 and 60 minutes, so maybe they called us and told us there was a delay, and it was only between 30 and 60 now. What would be the height? It would become 1 out of 30, because if I told you I've now changed it and it's going to happen sometime in this 30-minute interval. Now the length of this is just 30, so the height becomes 1 out of 30, the probability. Does that make sense? If I said it was between 15 and 20 minutes. Yeah, there's only a 5-minute window, so the probability anywhere would be 1/5. All right. So the height is just 1 out of the length of your interval. Using this, what would be the probability that they show up between 15 and 30 minutes? So if we think about this, the probability is really just the area under this, in this rectangle, right? If we're going to be between 15 and 30, find the area of that rectangle? Length times width. So the length of this between 15 and 30 minutes is 15 times, what's the height of my rectangle? 1 out of 60. So if you're going to be in that 15-minute window, 15 times 1 out of 60 gives us 0.25. So there is a 25% chance they show up in that 15-minute interval. All right. Questions on that? Okay. Next one. There is a 30% chance your package will arrive in the next blank minutes. So this is kind of working backwards. If it's a 30% chance, the probability is 0.3. Think about how we found the probability up here. We took the number of minutes. It was a 15-minute window. Do I know how many minutes here? So I could call it x. Times, what's the probability anywhere in that interval? Equals, if it's a 30% chance, my probability is 0.3. Yep. Multiply over your 60. So we would have a 30% chance that it happens in the next 18 minutes. So we've seen graphs that look kind of like this before. We called them bell-shaped, right? So it turns out if things are relatively bell-shaped, they are the shape of the normal curve. This one, you know, it's kind of broken into rectangles, but what happens as we get more and more rectangles? It's going to get more precise. The more rectangles we have, the more like a perfect curve it will look. So a normally distributed function is going to look like a bell curve, okay, nice and symmetric. Remember when we talked about these before, we said the middle is the mean, and back when we did the empirical rule, we said, you know, you can measure one standard deviation, the mean plus the standard deviation, the mean minus the standard deviation. So that was all dealing with a normal curve. Some properties about this. It's symmetric around the mean. Okay, you have the same amount on both sides. 50% is above, 50% is below. It's perfectly normal. The mean, median, and mode are the same. It has a single peak, and that is the mean, median, and mode. Remember we talked about if it's skewed, that's when the mean and the median didn't match. We talked about that back at the beginning. So that peak is your mean. The total area under our curve is 1, because it is the probability, and the empirical rule is still true. So remember that empirical rule we talked about at the beginning? It said, gave us percents of our data that fall within 1, 2, and 3 standard deviations of the mean. For example, let's say I threw a curve up here. We're going to do another one like this in a second. But if I said this was the curve, and this was a normal distribution, can you tell me what the mean of this is? 7.5, it's the center. The standard deviation is how far from the mean to 1 point away. 9 minus 7.5 is 1.5, or you could do 7.5 minus 6, it's 1.5. All right. I just put the empirical rule up here again. We've talked about it before, but it is still true, so just kind of a refresher there. Remember, it was 68% was it within one standard deviation. Since it's normal, it is a 50-50 split, so half above, half below. 95% was within 2 standard deviations, so half on each side, 99.7 within 3. So looking at this, does this graph appear normal? So we don't know for sure, we don't have all of it, but when we're looking at normal, we're looking at, is it bell-shaped? So is this graph bell-shaped? Yeah. Yes, so we would call that normal, as best we can say from this graph. If it's skewed, then we would say it's not normal. So this one is bell-shaped, so that's normal. What would be the mean of this graph? 2. The mean is just your peak. So if we look right there, that is 2. A standard deviation is how far from 2 you would go in either direction. Standard deviation is 3. You do 5 minus 2 or 2 minus negative 1. Let's take a look at this one. Both of the graphs shown have a mean of 10. One has standard deviation of 3, the other has a standard deviation of 2. Determine which is which. How do we know both of these have a mean of 10?
Their middle's line up.
That's where the peak is. Okay. So we have graph A, graph B. We're basically trying to figure out what the standard deviation of each is. One of them's 3 and one of them is 10. Or sorry, 2. Alright, standard deviation is how far you go until your graph starts curving outward, right? When you have a smaller standard deviation, what does that do to your graph?
Go wide.
The smaller the standard deviation, it would be skinnier. So let's think about it this way. Alright. So this is my graph. If I compare that to another graph, this red one is more spread out. Would you agree with that? Remember, standard deviation is a measure of how spread out your points are. So when my points are more spread out, that spreads out the whole curve. That means there is a higher standard deviation. When all my points are close together, it makes my curve get skinnier because they're all about the same, and that's a smaller standard deviation. So when I'm looking at this, the bigger standard deviation is the wider curve. So which of them is wider? B. That one comes out further. So it has to have a higher standard deviation. So that one would have to be the standard deviation of 3. When I look at A, it's more skinny, so it has a smaller standard deviation. So that's 2. Okay, so just remember, bigger standard deviation, more spread out. So it'll be a wider curve. Interpretations, when we are talking about a normal curve, the area under the curve can be interpreted a couple different ways. We could say it's the proportion of the population with a certain characteristic, or the probability that a random individual will have the characteristic. For instance, if I were talking about the probability of blue eyes, and I said it's 0.45. That means approximately 45% of the population has blue eyes. Or if I pick one individual person, the probability they have blue eyes is 45%. So you can think of it 2 different ways. The probability one person would have it, or in what percent of the total population has it. So final example of the day. Short day to start us off. The weight of giraffes are approximately normally distributed with a mean of 2,200 pounds, standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. So normal curve just means bell-shaped. The peak is your mean, which was,
220.
and where the graph kind of starts flipping out or turning outward. Well, my graph is not very pretty. Hopefully yours is better. So that's, my standard deviation was 200. So this point would be 200 higher. And this one would be 200 lower. Okay, we could label more standard deviations. At the very least, if I ask for this, I want at least one standard deviation labeled. You could do 2 or 3 if you wanted, but 1 is sufficient. Part B. Shade the area under the normal curve to the left of x equals 2,100 pounds. So 2,100 would fall in between these two. And we are just shading everything to the left of that. Part C. Suppose the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide 2 interpretations. So you are just writing 2 sentences for how this could be described. So one option is it's a probability. This is talking about the weights of giraffes, right? So I could say the probability a giraffe weighs, what am I looking at? I'm not saying the probability it weighs 2,100 pounds exactly. Less than 2,100 pounds is 0.3085.
We should do it.
Sure. The other option, instead of saying the probability of 1 giraffe, what could I say?
There's a 30.
That's still kind of talking about 1. But I could talk about it as a percent of the whole population, right? Remember I said, like with the blue eyes, I could say 45% of all people have blue eyes. Or in this case, I could say 30.85% of giraffes weigh less than 2,100 pounds. So, key things from today. We've talked about symmetric and bell-shaped throughout the semester. It's come up. Now we are learning there is a name for it. That is called a normal distribution. Empirical rule still applies. It's that nice bell-shaped curve. Half of it up below the mean, half of it above the mean. Okay. Any questions?